Stability of fixed points. For an ODE system, in this form, here x derivative equals vector field, capital X. If we're solving a system and relatively easily, we can find constant solutions by setting the capital X to 0. So if we can find all solutions of this equation, then we can find our constant solutions. So where P is a constant vector, then a solution of this form will be called a fixed point, also called an equilibrium solution. So in this video, I want to talk about stability of a fixed point. So how do we know a certain fixed point is stable or not? Depends on the definition. What do we mean by a stable fixed point? So here definition. So the system is stable at an equilibrium point P if for any positive number epsilon, there exists a positive number delta such that for all solutions x t with this initial data, that that is whenever the initial data is this close to P, then the solution curve will be this close. So we need to change one number. This is delta. So what does that mean? This is a definition, just like in calculus, the epsilon delta definition. This is true for all t, for any t. So in this definition, we define an equilibrium point as a stable equilibrium if for any given positive number epsilon, here, any positive epsilon, there exists a positive number delta such that the solution. So I want to remember what that means. That is actually one of the solutions to the system. So remember, there's the system, and also this satisfying the differential equation. Maybe there are many solution curves, but we want to give additional requirement. That is, at a certain time, we hope the solution curve will pass through this point. So that will become an initial value problem. So this initial value problem, it has a solution. So if we have a curve that will pass through this point satisfying the governing equation, then we denote that solution curve as it's just a curve, right, as a function of t, a vector valued function of t, passing through, satisfying the initial data. So that's just a notation here. So you see this, this one is a notation, means solution for the initial value problem. So that is that solution curve. So this curve, basically what it says is this solution curve can be sufficiently close to the fixed point as long as the initial data is close enough to the fixed point. So in that case, the fixed point is called stable, a stable fixed point. So now we have this definition, but there are, if we give more description of the stability of a fixed point, then we can further classify the stability into two kinds. One, so if the system is stable and also satisfying additional feature, then we call it asymptotically stable. So the system is asymptotically stable at an equilibrium point P. If it is stable at P, and if the the solution curve satisfying that initial data, so the solution curve is approaching P. That means the distance from the solution curve and the fixed point is approaching 0 as t goes to infinity. So this, so that means the system is not only stable, the solution curve will be getting closer and closer to the fixed point as time increases. So this is the first kind of type of stable. And in this case, obviously the P, you see, you can imagine some solution curve like a spiral and getting sufficiently close to this point P. So P is called an attractor. P is called attractor. If we have stability, we have a asymptotically stable system. So in this case, P is an attractor. There's another case. So when it's stable, if it's not asymptotically stable, then it is neutrally stable. So there's another possibility. So still under the category, the stable, but not asymptotically stable. So it's called neutrally stable. It's just that is a system. So to define this one, it is very easy as long as it is the system is the system, which is this one, is stable, but not asymptotically stable. So if we try to look at some concrete cases, for example, in the previous case, asymptotically stable, first of all, it has to be a stable case, right? So the system is stable. That means if we have a point P, suppose you want this is the epsilon neighborhood of point P. And what is stable? That stable means we can find a delta. So delta, there exists a certain delta. As long as your initial point, your initial value, so suppose this is a delta. So this delta. So as long as your initial value in the delta neighborhood of P, so here is an initial value x naught, your initial value in the delta neighborhood of P, then the solution curve, let's draw a solution curve passing through this point. Then the solution curve will be in the epsilon neighborhood of P. Right, so your solution curve can be, something. So this is a definition for a stable system. But in this definition, it could be asymptotically stable. It could be neutrally stable. So asymptotically stable is quite strong. That means, in addition, it is stable. Also, the solution curve will eventually getting closer and closer to the fixed point. That means it will approach the fixed point when t is increasing. So the solution curve will be getting closer and closer to the fixed point P. So that case, P is called a attractor. But if you look at the neutral stable, we don't require that. The neutral stable means it is not asymptotically stable, but it is still stable. So let's try to show a case that is neutrally stable. Suppose I have a fixed point P. Suppose we have some periodic solutions. Periodic solutions. So this case is actually to describe this neutrally stable. That means when the initial data is close enough to P, then the solution is close enough to the point P. So, but each solution curve is not necessarily approaching to P when T goes to infinity. So this case is neutrally stable. So you can pick, for example, one curve. For example, this initial data. Yeah. So when the initial data is this close to P, and the solution curve, right, overall solution curve is also close enough to P. So it satisfies the definition for a system to be stable. But each solution curve, if you look at the solution curve with this initial data, it doesn't approach P. That means the difference from this solution curve and P is not approaching zero, right? That's not true as T goes to infinity. So this is not asymptotically stable, but it is neutrally stable. So after we know a system being stable, then what is unstable system? So whenever the system is not stable, then it is unstable. So we can classify systems into stable and unstable. And if it's stable, the fixed point, right, could be an attractor. And if it's asymptotically stable. A system can be neutrally stable. So now let's look at a concrete problem. So in this system, we have three equations, and derivative of x, y, and z. And the first equation is this. Second equation, 20x. And the third equation Okay, we have three equations. So we can immediately see a fixed point because by observation, we can immediately notice a zero of the vector field, right? This, if the x is 0, y is 0, that's our fixed point. Yeah, fixed point, 0, 0, 0. So this fixed point, if we want to determine, this is our P in our, this P, just for now, we use it to denote a fixed point. So if we want to look at this 0, 0, 0, we want to decide whether the system is stable at this fixed point or not. And then we can do some analysis. The analysis is we want to look at nearby solutions. That means a solution curve right other than this point. Are they being attracted, or are they sufficiently close to this point when the initial data is close enough? So we just want to see whether the 0, 0, 0 is a stable fixed point. So let's try to look at another solution and this solution and the distance between them. So that means we want to measure the distance. That's the norm. So we just want to, let's give a name to this distance. That is R. And we can immediately write, which is x squared plus y squared plus z squared. And take a square root. That's the distance. And we want to see whether the distance is approaching to 0, right? The distance between the two. If it's approaching to 0, that means the solution curve is approaching to the fixed point. So that is our some work we want to do. So then we're going to look at this distance function. If we take a derivative by the chain rule, you see this is a derivative with respect to t. So using chain rule, it's a half of the x squared, y squared, z squared to the negative half. And continue to use chain rule. So that's a 2x, x derivative, plus 2y, y derivative, plus 2z, z derivative. And then we can continue to write this as, because the half and 2 can be canceled. So, and this part is simply the reciprocal of r. You see, this is r with the negative half power. It's a reciprocal of r. So we can write this 1 over r. 1 over r. So now what do we have here? So x times x derivative. So x times x derivative, notice in the equations, x times this, right? So and y times y derivative. So y times this. So the derivative can be replaced, and z times z derivative. So z times this. And so we can replace all the derivative, and eventually we can write this part into in terms of XYZ only. So no more derivative. So after we go through that substitution, that means X prime, Y prime. So this is our X prime, Y prime, Z prime. And then we can immediately, by substitution, we get X times X prime. So finally, it is this quantity. Yeah, after you take some time, and then we can get this quantity. And now notice we can rewrite this quantity as negative r squared, right? So we have still have 1 over r. This is negative r squared. This is a negative 0.1 r squared, r to the fourth. So right now what we have is, okay, we can just further simplify a little more, because r squared divided by r to the fourth divided by r. So we can finally write the right-hand side is just a negative r minus 0.1 r to the third power. So left side is r derivative. So we have this equation. Now the r derivative equals negative r minus 0.1 r cubed. So, and we can discover what happens to this distance. So this distance r satisfying this differential equation. So let's go ahead, do some more analysis. So remember so far we have negative r, negative 0.1 r to the third power. So if, of course, this is a nonlinear equation, it's possible to solve if you try to get r as a function of t, right? Separation of variables method, for example, possibly we can solve this. But if we pretend this is a linear equation, we can isolate these terms. Of course, it's not a linear equation because we notice r to the third power. So it's not a linear differential equation. But although it is nonlinear, we can still apply the integrating factor. For example, multiplying both sides by the integrating factor, which is the e to the 1. Remember, this is a 1, number 1. So the integrating factor is e to the integral 1 dt. So it's just the e to the t. So we use that e to the t, and we multiply both sides of the equation. So we multiply both sides of the equation by this e to the t. And then the left side will become e to the t times r derivative. And the right-hand side, after you multiply by e to the t, so it's going to be this. So that after you multiply integrating factor to this both sides, then we can see the left side becomes one single term. So that's a little bit easier for us to see this quantity. If its derivative is negative, then this quantity is decreasing. So we can immediately conclude that this quantity is decreasing. Is decreasing. So if it's decreasing, then we can look at this compared to the when t is 0. When t is 0. So because it's decreasing, yeah, why is decreasing? Since the derivative is negative. You see, exponential function is positive, r is positive. So the derivative function is negative, therefore the function is decreasing. The function is decreasing, therefore the larger the t, the smaller the function value. So from here we can see the RT and we divide e to the t both sides, so we get e to the negative t. And this is 1, right? R to the R0. That means initially, if the solution curve is that close from the equilibrium solution, then with time, the distance of the solution curve from the equilibrium solution will be decreasing to 0. We see the exponential decay function e to the negative t. It is going to go to 0. So here we see that r of t is decreasing to 0. So therefore, it is asymptotically stable at the equilibrium point 0, 0, 0. Because we just proved that any other solution curve, x, y, z, right? The distance is approaching 0 as t goes to infinity. So that's our r. So we have shown that this r is approaching to 0 for any solution curve. Yeah. So approaching to that fixed point as long as time goes to infinity. So it's a globally asymptotically stable. Yeah, stable. And for this problem. So we have a system, and we just proved that this system is asymptotically stable at a fixed point, which is origin. And if you really want to look at the situation, we can try to imagine that point 0, 0, 0 is here. So suppose you have a solution curve. Suppose starting from here, initially, that's how far it is from the fixed point, right? This fixed point is denoted by P. And then this is the initial data of a solution curve. But then no matter what the initial data is for this system, we notice that it will, as time goes on, this x this is actually our vector-valued function in the three-dimensional space. So we can put this as still to indicate this is the initial point. Put a little zero. Yeah, this starting from here, but as time, this will approach to P. This means R with time, it's getting smaller and smaller. So the distance of the solution curve from solution curve to the P is approaching zero. So that is a graphical explanation of this stability. And here we have an asymptotically stable fixed point.